Okay, we've studied Markov chains. We've convinced ourselves that the Markov assumption was reasonable in our application of the Markov chains to the CPG island recognition problem. Now it's time to meet a more sophisticated kind of probabilistic model that also builds on the Markov assumption, which is called the Hidden Markov Model. And let me just motivate it at the beginning with a little bit of an example. Let's just say I'm walking past my local baseball stadium. So I live in Baltimore. The local baseball team are the Baltimore Orioles. Here's a picture of their stadium. And let's say there's a game going on. So let's say inside the stadium, there's a baseball game happening, but I'm just walking by. I don't know necessarily whether the Orioles, which is the home team, are winning or not. But maybe I can hear noises coming from inside the stadium as I'm walking by. Maybe the noises are happy noises like people cheering and clapping. And that's a hint that, of course, maybe something good is happening in there. So for the home team, in other words, maybe the Orioles are doing well. And therefore, maybe I would predict that the Orioles are winning the game, right? So maybe. It's not a direct indication that they're winning the game, but it's an indirect indication that they may be winning the game. And likewise, of course, if I hear silence or booing or some other negative sound coming from inside the stadium, I could infer the opposite. I could maybe infer that the Orioles are losing or not doing so well. But importantly, these are only indirect signs about what's going on inside the stadium. If I were inside the stadium, I could see the scoreboard and I could see exactly which team is winning and by how much. But because I can't see inside, because I'm outside the stadium, I can only go by these hints. The sorts of problems we solve with hidden Markov models are these kinds of inference problems. There is some system that has some state, some configuration, right? The baseball game is happening and there's some score currently in the baseball game. But I can't directly observe that information. I can only observe indirect information that's coming out of the system, like in the form of the sounds in this example. And I can use those to try to infer what's happening inside. But what's happening inside is hidden. So hence the hidden Markov model. There's a part of the situation that is just not known to us. So to get more to the probabilities and the mathematics of the hidden Markov model, let me now switch to showing you this diagram. It's sometimes called the Trellis diagram. And what it's meant to show are really the two components of the hidden Markov model. The internal state of the thing that we're studying, which is represented by these nodes that are labeled P1 through Pn, and then the things coming out of the system that we can observe. These are called the emissions, and these are represented by x sub 1 up to x sub n. Usually, but not always, the system is thought to be, the system that we're modeling is evolving over time in discrete steps so that our model is capturing what's happening at each of those time steps, which is what's happening with the horizontal dimension of this picture, right? This is the state of the system at step 1. This is what we observe at step 1. This is the state of the system at step 2. This is what we observe at step 2. And so we could be applying the hidden Markov model to study something like the weather, right? So maybe step 1, 2, 3, and so on. Maybe these are days on which we want to predict the weather, and we're using information from previous days to predict future days. Maybe we're studying a chess game, right? So these steps are just the turns of the chess game. So again, the steps sort of correspond to time, right? How the system is evolving over time, how the chessboard, the state of the chessboard is evolving over time. However, it doesn't have to represent time, and in fact, it won't for the examples that we care most about, right? We're trying to apply hidden Markov models to analyzing sequences, and for sequences, it's not time that's evolving, it's position. It's where we are looking at our sequence, right? So instead of time, we're sort of using this dimension for space. We're moving along the DNA molecule, reading each of the nucleotides, and that's what this subscript is referring to. It's referring to our position in the molecule. Okay. So for a bit more formality, let's think about these X's and these P's that are on the screen right now. We can think of these in probabilistic terms. These are random variables, these P's and these X's. And each of the X's are strung together in a sequence of emissions. Emissions, meaning something is coming out of the system that we can observe. Something's being emitted from the system that we can observe. And each of these random variables, x sub 1 up to x sub n, they can take a value from some set sigma. Sigma is just the set of things we might observe, right? So if we're walking by the stadium, maybe sigma is silence, cheering, or booing, or something like that, right? Distinct things that we might be observing that might be coming out of the system that we're studying, okay? So these things take on some value from that set sigma, and they are called the emissions. Those are the x sub i's. And then the p's, and I'm drawing the circle around each of the p sub i's is a dotted circle. That's just to reinforce the fact that this is not something that we can directly observe. But we do know that the system is in one of a few discrete number of states, right? The system can be in one state or another, or maybe a third state or something like that. So in the baseball example, maybe the states we're concerned with are the Orioles are winning, the Orioles are losing, or it's tied, right? So maybe there's 3 states. And that's the thing that we can't directly observe. Again, we have to infer it because we are outside the stadium and we can't see the scoreboard. If it's the weather, then maybe the P's are what exactly is the state. Is it sunny, partly cloudy, raining, etc. So these P's are states. And a sequence of states we sometimes call a path, right? Like a path is more like a complete description of how the system evolved over time steps or space steps. Okay, and each of these p sub i's can take a value from some set which we usually call capital Q. So Q is the set of possible states that we could be in at any given time. And once again, these p's are not something that we can observe, right? These are the hidden part of the hidden Markov model. And these states are connected by transitions, edges, right? So I'm going to use those two interchangeably, but I'll try to use the term transitions, which is a little bit more compatible with thinking about states. So there's two kinds of transitions in this diagram. There's the vertical ones and the horizontal ones. The vertical ones are pointing from p sub I to x sub I. So it's connecting each p with the x in its same step. Okay? And then the horizontal ones are connecting successive p's. So it's connecting p sub I to p sub I plus 1, and so on. Okay? So these transitions, just like with the Markov chains, these transitions convey conditional independence assumptions. Right? Unlike with the Markov chains, we really have two different kinds of conditional independence assumptions here because we have the vertical edges and the horizontal edges. So let's just focus on one of the vertical edges for now, like that one right there, connecting p sub 2 to x sub 2. And what that transition is conveying is that x sub 2 is conditionally independent of everything else, all the other random variables in the whole lattice, given p sub 2. Okay, so let's just remember what conditional independence does and does not mean. So it does not mean that x sub 2 is independent of, let me pick another, for example, that x sub 2 is independent of p sub 1. Right, that's not true. Those do have a dependence with each other. However, what we're saying is if you tell me p sub 2, it doesn't tell me anything in addition if you also tell me p sub 1. Let's look at one of the horizontal edges, like this one right here. This is another conditional independence relationship, and it's saying P4 is conditionally independent of everything else given P3. Right? So if you tell me P3, that in some sense tells me all I need to know about P4. It doesn't tell me anything in addition if you tell me P2 or X2, etc. So just like with the Markov chain, what these conditional independence assumptions, which are Markov assumptions, what these conditional independence assumptions allow us to do is to compute joint probabilities by multiplying together a bunch of simple conditional probabilities. All right, so again, we can think of the multiplication rule, which lets us take a big joint probability and factor out pieces into conditional probabilities. And then we also bring in the Markov assumption, in this case represented by all the conditional independence relationships that we've drawn in the diagram. And those simplify the conditional probabilities so that the right-hand side of the bar only has one variable on it. Right, so if we want to compute a joint probability, the joint probability of some path and emission sequence, some complete set of p's and a complete set of x's, if we want to compute that joint probability, the way we would do it is we would multiply together all the conditional probabilities in this picture and one marginal probability. Remember, when we use the multiplication rule, there's always this one last term at the end, which is not a conditional probability, it's just a marginal. And in this case, the marginal probability is going to correspond to the probability that we begin in some state, in state p sub 1. Okay, but the important part is, again, the joint probabilities, which would otherwise be kind of complicated and hard to work with, have here been decomposed into products of simple conditional probabilities of two kinds, right? The vertical kind and the horizontal kind. Okay, so if we wanted to compute a great big joint probability of a path and an emission sequence, so this is the probability of p sub 1, p sub 2, all the way up to p sub n, and x sub 1, x sub 2, all the way up to x sub n, so that's the states, and then the emissions. We could do it by forming a product, and we can think of these the terms of this product as being of three kinds. There's all the conditional independence relationships that are vertical in the diagram. So those are the probability of an emission given that you're in a particular state. And so we'll call these emission probabilities, these conditional probabilities. So there's all the possible emission conditional probabilities. We have to multiply all those together. We have to multiply all the red vertical transition together in order to compute the overall joint probability. Okay? And those probabilities we're going to think of as being written down in a matrix that we call E. E for emission matrix. Right, I wrote it over here. So E is just a matrix that holds all those conditional probabilities. Just like in the previous lecture, we saw tables that held 16 conditional probabilities for every possible base and previous base. This emission table is going to be all the conditional probabilities for every possible emission given every possible state. Okay, so we multiply those. We have to then multiply in the blue transitions, and those conditional probabilities are going to be encoded in another matrix, which we call A here, the transition probability matrix. This matrix just holds all the conditional probabilities that are state given state. You know, what's the probability that I end up in some state given that I was in some state in the previous step? Right, so all possible such combinations of two states are in this matrix A. And then the marginal. And the marginal you can think of as just a vector. It's not a matrix because there's really just one probability per state, right? So it's just like a vector parallel to all possible states, holding the probability of starting in any one of those states. Okay, so we just call that the initial probability vector or array. Okay, so to get a joint probability in a hidden Markov model, we just have to multiply all these things together. The emission conditional probabilities, the transition conditional probabilities, and then one marginal. at the end. So just to solidify this before we wrap up this lecture, let me give a concrete example. And this is a commonly used example for hidden Markov models. And it's a really good one because it's both simple and it uses all the components of the hidden Markov model. And this is an example that's used in the book that I pointed to in the first lecture. These lectures are mostly based on, but it's also used in other books. For example, I teach out of this book as well, An Introduction to Bioinformatics Algorithms by Neil Jones and Pavel Pevsner. And so it's a common and well appreciated example. Okay, here's the example. It's kind of a word problem. So say you're at a casino, and this casino is, I'm sorry to say, a very boring casino because the sorts of games that they have to play include the following game. Okay, there's a table where a dealer is repeatedly flipping a coin. And sometimes when the dealer is doing this, they're doing it with a coin that is fair, which is to say the coin has equal probability of landing heads or tails. So 0.5 probability of heads, 0.5 probability of tails. But sometimes, invisibly to you, right, the dealer is very good with sleight of hand, they can switch between the fair coin and another coin, which is a loaded coin. And the loaded coin does not have equal probability of heads and tails. Instead, it has a greater probability of heads. So the probability of heads is 0.8, probability of tails is 0.2. And in between each of these coin flips, the dealer might switch from one coin to the other. Right? It's sort of the dealer might switch between one or the other with some probability. And so we say that the dealer switches coins with probability 0.4, which means he sticks with the same coin with probability 0.6. Okay, so this is the setup for the occasionally dishonest casino. Again, this wouldn't be a very fun game to play, but if you were playing this game and you wanted to win, right, you wanted to come away with more money than when you started, then the real trick would be trying to figure out which coin the dealer is using. All right. Okay, so in some sense you can't really do that because there's no, again, the dealer switches invisibly. But if you gave me a sort of history of what were all the outcomes of all the coin flips, I could maybe make an educated guess as to when the dealer was using the fair coin and when the dealer was using the unfair coin. We'll get more to that in the next lecture when we talk about decoding. But in this lecture, we just want to use this word problem to set up all the conditional probabilities and that we would need to fully define the HMM. Okay, so just to picture what's happening and relate it back to the trellis diagram we saw at the beginning, we can think of the state space, we can think of the state of the system that is hidden to us as being the loadedness of the coin, whether the dealer is using the fair coin or the loaded coin. And in this picture here, I'm just using the size of the heads and tails to denote that there's a period in the middle there where the dealer is using a loaded coin, but the dealer is otherwise using a fair coin for the coin flips that are visible on the screen right now. So in other words, I've told you the hidden thing, right? The hidden thing I've just went ahead and told you as though we knew. And then there's the emissions, and the emissions, of course, are the outcomes of the flips. So we always get to see those. We get to see whether the coin comes up heads or tails. We'll just use H for heads, T for tails. And so in this sort of specific instance of the trellis diagram, the hidden state is the loadedness of the coin, and the emission is the heads or tails. Okay. So let's go ahead and fill in every conditional probability that would make up the HMM for this casino, this occasionally dishonest casino. And that word problem, which I will now bring back, right, the words of the word problem, give us everything we need to know to fill in every probability in all these tables. Actually, I had to add one more sentence there at the bottom because I need to tell you about the initial probability of the dealer using the fair coin or the loaded coin. We need that for the I vector. But with what's on the screen right now, we should be able to fill in all three of these data structures over here, this, and this, with all the parameters of our HMM. Okay, so let's start with the one labeled A. A is the transition probability matrix. So A corresponds to what we drew as the horizontal transitions in the Trellis diagram. The probability that you are using a fair, or the dealer is using a fair or loaded coin in step I, given the coin they were using in the previous step I minus 1. Okay, this is given by the word problem, because the word problem says between each flip, let me underline it, between each flip, the dealer switches coins invisibly with probability 0.4, which means that the dealer sticks with the same coin with probability 0.6. And in this table, these two diagonal entries correspond to the situation where the dealer sticks with the same coin. Right? So those two entries should both get a 0.6. 0.6. 0.6. Whereas the two off-diagonal entries correspond to the situation where the dealer switches coins, which the word problem directly tells us that probability is 0.4. So we want to put 0.4 in both of those. Okay. Fantastic. So those are the transition probabilities, conditional probabilities, right? Probability of fair given fair, fair given loaded, loaded given fair, loaded given loaded. And now let's move on to the next matrix, which is the E matrix, the emission conditional probability matrix, right? We want to know what's the probability of heads given fair, heads given loaded, tails given fair, tails given loaded. That's also given in the word problem, right? We say for the fair coin, probability of heads and tails is 0.5, but with the loaded coin, probability of heads is 0.8, so probability of tails is 0.2. So we know we should fill in, okay, heads given fair, that's 0.5. Tails given fair, it's also 0.5. Heads given loaded, that's 0.8. Tails given loaded, that's 0.2. Okay, that's just direct from the word problem. And finally, we have to fill in the initial probabilities of fair and loaded. That was given in this last sentence here. That's 50-50. So this would be 0.5. 0.5. There's a point down there. Okay. There we go. So that's what a hidden Markov model is. That's how we could populate all the tables of conditional probabilities that make up the hidden Markov model. If they're all given, it's not realistic to think that they're all given. I think you'll agree. So we also have to think about how to infer some from others. We also have to think about how to train these things from examples. All of that is yet to come. But what comes next is what we would call the decoding problem. So in other words, if you're in the casino and you have seen the dealer use the coin many, many times, and you want to predict in the last step that I just saw, was the dealer using heads or the fair coin or the loaded coin? Well, that's a decoding problem, so we need to cover that next. So we'll see that in the next video.